Hello and welcome to online lecture number 12 for Chemistry 1101 during the spring semester of 2020. In this lesson, we will finish Chapter 9. Chapter 9 has all been about solutions, understanding ultimately their properties, and finally we'll get into understanding what kinds of properties we can predict based upon the concentrations of these solutions. So as you saw before, many solution properties, perhaps even most solution properties, depend upon both the identity of the solute and its concentration. And this is just a short list of the many. But it turns out that some properties of a solution only depend upon the concentration of the solute. And these are what's referred to as colligative properties. And there's several colligative properties. The colligative properties we'll talk about specifically are the freezing point of the solution, the boiling point of the solution, and a phenomenon known as osmosis. So these are properties that depend upon the concentration of the solute, and specifically, they depend upon the osmolarity of the solution. So that's what we're going to use to be able to predict the relative freezing points and boiling points, as well as explain osmosis for various solutions. So first up is freezing point. And it turns out that the freezing point of a solution is always lower than that of the pure solvent. A solution always freezes at a lower temperature than that of the pure solvent. So a saltwater solution, for example, will have a lower freezing point than that of pure water. And the decrease in freezing point, how much lower the freezing point of the solution is compared to the solvent, that's dependent upon and proportional to the osmolarity of the solution. And there are equations that actually allow you to calculate what that freezing point would be of a solution, but we're more interested in just relative comparisons of the freezing point of one solution compared to the freezing point of a second solution. So notice with osmolarity, the higher the osmolarity of the solution, the lower the freezing point will be. And we take advantage of this in several different ways. One is to sprinkle salt on our sidewalks or roads during the wintertime. The idea there is that when it snows or freezing rain, it mixes with the salt, makes a salt solution, and then that snow salt or freezing rain salt mixture, because it's a solution, because it is a mixture, has a lower freezing point than that of the pure rain or the pure snow. So as a result, it will freeze at a lower temperature. So the temperatures are below freezing, below 30 degrees Fahrenheit or 0 degrees Celsius, but not too far below the freezing point. A mixture of salt and water or salt and snow will stay mostly liquid, whereas if it were just pure snow or pure ice, it would freeze. So it's a lot more dangerous. So the idea is we want to be able to determine, as I said, just compare relative freezing points, and we want to decide which of these two aqueous solutions has the lower freezing point. The one with the lower freezing point would be the one with the higher osmolarity of the solution. So ultimately, like we saw in the previous chapters, when comparing the boiling points or densities of pure substances, if the question is about boiling point or density of pure substance, it's really a question about IMFs. Likewise here, if the question is about the decrease in the freezing point of a solution, it's really a question of osmolarity. And whichever of these two solutions has the higher osmolarity, that's the one that will have the lower freezing point. So we have our two solutions, 0.1 molar sodium chloride or 0.1 molar C6H12O6. The question is determine which of these two solutions do we expect to have the lower freezing point. And as we just learned, the lower the freezing point is associated with the solution with the higher osmolarity. So really the question is between these two solutions, which one has a higher osmolarity, because that's the one that's going to have the lower freezing point. So to determine osmolarity, we'll take the molarity and then multiply that by the number of dissolved particles produced when the substance dissolves. So sodium chloride as an ionic compound will break apart into two particles, sodium ions and chloride ions. So as a result, its osmolarity will be equal to the number of dissolved particles 2 times the given molarity for an osmolarity of 0.2 osmoles per liter of sodium chloride. So that's the relevant number when trying to predict these relative freezing points. For 0.1 molar C6H12O6, notice it's a molecular compound composed of all nonmetals. So as a result, molecular compounds, when they dissolve, 1 mole of any molecular compound when it dissolves produces the same number, 1 mole of dissolved particles. Because the molecules themselves remain intact, they just separate from each other. They break those intermolecular forces that were holding them together in the condensed state, a solid or liquid phase. So in this case, the osmolarity of this substance, this solution, equal to 1 times its molarity, to give us an osmolarity for molecular compounds, which is always the same number as the molarity. So now we have our two numbers to compare. And so even though these two solutions are the same molarity, because this solution is twice the osmolarity, 0.2 osmoles per liter versus 0.1 osmoles per liter, and because it's osmolarity that determines the freezing point of the solution, the higher the osmolarity, the lower the freezing point, we can predict that this solution, relatively speaking, should have a lower freezing point. So as we go through these examples, keep in mind that's how we're always going to apply. We're going to determine osmolarities and then associate the difference in osmolarities to a difference in freezing point, and then later boiling points and even this phenomenon of osmosis. In our second example, we'll compare a 0.2 molar magnesium fluoride solution to a 0.8 molar C6H12O6 solution. So for magnesium fluoride, ionic compound, as such, you'll break apart into two types of particles, cation and anion. Specifically, they produce 1 magnesium ion and 2 fluoride ions. For a total, though, notice, of 3 particles. So it's our osmolarity will be equal to resolved particles, 3, times the molarity, to give us an osmolarity of 0.6 osmoles per liter of magnesium fluoride. So that's the osmolarity solution. That's the number that's relevant when predicting freezing points, and as we'll see later, also boiling points. With C6H12O6, this is the same example we saw previously. Like any molecular compound, because it produces 1 mole of solute particles for every 1 mole of solute, the osmolarity is the same as the molarity. So we get an osmolarity of 0.80 osmoles per liter of the C6H12O6. So the relevant numbers are not the molarities, but rather the osmolarities. Because this solution has a higher osmolarity than this solution does, we'd expect this solution to have the lower freezing point. In our final example for determining relative freezing points is to compare a 0.35 osmolar potassium sulfate solution to a 0.25 molar potassium hydroxide solution. So notice that we're already given osmolarity here, so nothing to do. We already have the number we're interested in. But for the potassium hydroxide solution, we're given molarity. So like before, we need to convert that to an osmolarity. Potassium hydroxide will break up into its cation and anion, 1 cation, potassium, and 1 anion, the hydroxide ion, for a total of 2 particles. So its osmolarity equal to the resolved particles 2 times the given molarity for an osmolarity of 0.5 osmoles per liter of potassium hydroxide. So now we have our 2 numbers that we can compare apples to apples. Because this solution has a higher osmolarity than this solution, we'd expect that the higher osmolarity solution should have the lower freezing point. So we saw with freezing point that the higher the osmolarity, the more concentrated solution is in terms of its osmolarity, the lower the freezing point of that solution should be. Boiling point is also a colligative property, and the effect on boiling point is the opposite of the effect on the freezing point. Because the boiling point of a solution is always higher than that of a pure solvent. And the relative increase, the absolute increase in boiling point is proportional to the osmolarity of the solution. So in other words, solutions that have a higher osmolarity not only will have a lower freezing point, as we saw on the previous slide, but also have a higher boiling point. And so the question is, which aqueous solution do we expect to have a higher boiling point? Once again, it's also really a question of osmolarity. Solution with a higher osmolarity has a higher boiling point. So compare these two, 0.1 molar calcium chloride and 0.24 molar C6H12O6. 0.1 molar calcium chloride is an ionic compound So break apart into two ions, two types of ions, calcium ions and chloride ions. But we need two chloride ions to have a balanced equation. Notice that calcium chloride breaks apart to 3 particles. So its osmolarity then will be 3 times the molarity of 0.1. It gives an osmolarity of 0.30 osmoles per liter of calcium chloride. For C6H12O6, as we saw before, it's a molar compound, so its osmolarity is always the same as its molarity. So in determining relative boiling points, we want to compare osmolarities. Notice that this solution has a higher osmolarity than this solution does. Even though the molarity is lower, that's not important. What's important is the osmolarity, because this number is higher than this number. Would expect consequently then that a 0.3 osmoles per liter calcium chloride solution should have a higher boiling point than that of the 0.24 osmoles per liter C6H12O6 solution. And in this example, we have a 0.30 osmoles per liter magnesium fluoride versus a 0.5 osmoles per liter of a methanol solution. Notice that here we're given the osmolarities already, so there's nothing to calculate. Compare osmolarities by themselves, and because this solution has a higher osmolarity than this solution does, we expect that this solution should have a higher boiling point compared to this solution, but both these solutions will have higher boiling points than that of pure water. So one application of this increase in the boiling point of a solution relative to the pure solvent would be antifreeze. Antifreeze is a very highly concentrated solution of propylene glycol and water, about 50% by volume. And we can see why we can have such a highly concentrated solution, why propylene glycol is so soluble in water. This is the structure, and notice that it has Lorentz dispersion forces, dipole-dipole forces, and it can also hydrogen bond with water, so like dissolves like. So as a result, because it can make such a highly concentrated solution, yes, it's called antifreeze, so its solution will have a very much lower freezing point than pure water would have. It freezes at negative 37 degrees Celsius, 37 degrees lower than that of pure water. But its antifreeze could also be called anti-boil because it boils at a much higher temperature as well, 129 degrees Celsius, about 29 degrees higher than that of pure water. So boiling point and freezing point both depend upon the concentration, specifically the osmolarity of the solution. The higher the osmolarity, the lower the freezing point. The higher the osmolarity, the higher the boiling point. And then third and final property or phenomenon we'll look at with regards to colligative properties and osmolarity is something called osmosis. And osmosis is a phenomenon, a very important phenomenon, where we have a spontaneous flow of solvent molecules, and because we usually are dealing with aqueous solutions, our solvent is usually water, and where the solvent molecules, and only the solvent molecules, are able to pass through a semi-permeable membrane. So the semi-permeable membrane only allows, it's semi-permeable, which means it only allows water molecules to pass, not the solute particles. And the direction of this flow of solvent molecules always goes from a solution of lower osmolarity to one of higher osmolarity. So we have this picture representing two different substances. On the right, we have to have a pure water substance, and on the left, we have some type of solution of water with these blue solute particles. So necessarily then what's on the left is more highly concentrated, it's higher osmolarity. So as a result, if we set this up with the semi-permeable membrane, over time, there'll be a net flow of water from the lower osmolarity side to the higher osmolarity side. The idea is that by solvent flowing and not solute, from lower osmolarity to higher osmolarity, nature is trying to equalize these concentrations. So by having water flow from this side to this side, the water level on this side will increase, thereby diluting the solution and making it closer to that of the concentration here. And so that will continue until either those concentrations are equal to one another, their osmolarities are equal to one another, or something called osmotic pressure builds up, and that's enough to stop this net flow. What we're interested in for our class, though, is just be able to predict when we have a semi-permeable membrane separating two different solutions, in which direction will we expect the water to flow. And it always flows from lower osmolarity to higher osmolarity, lower concentration to higher concentration. So very important applications of osmosis has to do with osmosis in cells, because the cell walls or the cell membranes that make up our animal cells or plant cells are in fact a type of semi-permeable membranes. So they allow water to pass through, solvent molecules pass through. And so if cells, intentionally or not, are immersed in a hypertonic solution, a hypertonic solution is a solution where the osmolarity of the solute is higher, hyper means higher, outside the cells versus inside the cells, where osmosis will occur through these semi-permeable cell membranes or cell walls. As a result, then water will flow out of the cells from lower concentration to higher concentration, water flow out of the cells. As a result, the cells will lose volume, and if they lose too much volume, they may shrink too much and actually die. So that's something we want to avoid if all possible. But we also want to avoid hypertonic solutions. Hypo means less, so this is a situation where these cells are immersed in a solution where the concentration of the solute, outside the cells rather, is lower than that of inside the cells. And so as a result, osmosis will occur. But in this case, osmosis will go from always lower to higher. Lower is outside, higher is inside. So there's a net flow of water into the cells. As a result, these cells increase in volume, and they may increase too much in volume, so they literally burst and die that way. What we like to do, we like to maintain what's called isotonic solutions. Iso means same. So this is a situation where the cells, their environment, are immersed in a solution that has the same osmolarity solute both inside the cells as outside the cells. And so if the concentrations, the osmolarities are already the same, there's no net flow of water either into the cell or out of the cell, so that keeps the cells healthy. This is especially important with IV administration. Typically, IV administration is done with so-called normal saline bags labeled NS. And they're labeled normal saline because they're solutions composed of sodium chloride and water, but specifically made up to about 0.9% mass per volume sodium chloride. And that number is important because that converts to 0.308 osmoles per liter. For our class, we're not worried about doing that conversion, but that's what it's equivalent to. And that number is important because that osmolarity is physiologically isotonic. So by using an IV bag and administering medicine or nutrients with that IV bag, it ensures, as that goes directly into the patient's bloodstream, that the patient won't suffer any ill effects due to either hypertonic solution or hypotonic solution, or rather everything's isotonic. So what we'd like to be able to do is predict the net direction of water flow in a osmosis setup. So if we have this picture, we have kind of a U-shaped tube, and the left side of the tube separated from the right side by a semi-permeable membrane, only allows solid molecules to pass either from the right to the left or left to the right. And on the side A, we have a 0.1 molar ammonium chloride solution. Side B is filled with 0.06 molar sodium phosphate solution. And the question is then, in which direction do we expect water to flow via osmosis? Here we have our picture. Side A, we have a 0.1 molar ammonium chloride solution. On side B, we have a 0.06 molar sodium phosphate solution. And we want to know that do we expect through semi-permeable membrane whether water should flow from side A to side B, or side B to side A, or in fact, maybe no net flow of water. And that's based upon osmolarity. Water solvent will always flow from the side of lower osmolarity to the side of higher osmolarity. So we don't want to compare molarities, but like with freezing point, boiling point, we want to look at osmolarities. So for ammonium chloride, we break apart into two ions, ammonium and chloride. So its osmolarity will be 2 times its molarity. Give us an osmolarity of 0.2 rather, osmoles per liter of ammonium chloride. So that's what's inside A. Inside B, we have a 0.6 molar sodium phosphate solution. Sodium phosphate as an ionic compound break apart into 3 sodium ions and 1 phosphate ion for a total of 4 particles. So the osmolarity will be 4 times its molarity. So an osmolarity then of 0.24 osmoles per liter of sodium phosphate. So as a result, now we compare our two numbers, osmolarity numbers. Notice that side A is lower osmolarity compared to side B. And in osmosis, solvent always flows from the side of lower osmolarity to the side of higher osmolarity. So in this case, we'd expect that there'd be a net flow of water from side A to side B. And we could set up this experiment and prove that this is actually what occurs, because then over time, we'd expect then, due to this net flow of water, that the volume on side A will decrease, the volume of side B will increase due to that net flow of water. And finally, some fun applications of osmosis. So our first example is pickling. Pickling, of course, is just a cucumbers that have been immersed in a saline solution for a very long time. And of course, most of us really like pickles, but we don't necessarily like cucumbers. And the reason why is that if you put cucumber, which is mostly water, it has a taste to it, but the taste is very dilute. But if you put it in a hypertonic solution, that saline solution that you immerse these pickles in, then over time, because of osmosis, water will flow out of that cucumber into its surroundings. As a result, then, what's left, the solute particles that give rise to the flavor of the pickle are able to concentrate. And so therefore, a pickle has a much more concentrated taste to it compared to a cucumber. Another example would be you can make your own fruit syrup, a process known as maceration. The idea is take fruit, fresh fruit, and just put a little bit of sugar on it, give some time, and because now that sugar creates a hypertonic solution outside of the cells of the strawberries or other berries, then water flow out of the strawberries into the surroundings, mix with the sugar, and then make its own fruit syrup. And then if you're really into eggplant, like my family is, typically the first step is to salt the eggplant, because eggplant sometimes has a bitter taste to it, but if you salt it, you add salt to the cut up eggplant, over time you'll see the eggplant begin to look like sweat as water is pulled out of the eggplant cells into the surroundings because of osmosis, because that salt creates a hypertonic environment relative to the conditions of the eggplant cells. And so that then allows you to, when you give some time, then you allow you to rinse off that salt and have a much tastier substance to begin with. Just some examples of osmosis and its applications. There's some fun examples as well as some much more serious examples. And with this, we finished chapter 9. Chapter 9 is all about understanding solutions and their behavior. And in the last couple of lectures, we'll get into the next chapter, chapter 10, where we talk about acids and bases and the important chemistry that concerns those substances.